here. Okay. It's an honor to be here and be giving the Ed Scott lecture. Ed was a good friend and a wonderful scientist, and this is a exquisite way to honor his many contributions to meteorite science. I'm going to talk about Mars sample return, and can you see my screen all right? I'm not sure. Is that okay? Okay. So we're going to look at Mars sample return, and I want to explain why meteorites and rover missions are not enough. And I don't know why I can't change the screen. Let's try it again. Okay. Mars sample return is tricky. We obviously cannot know precisely everything that we will discover. If we did, we really wouldn't need to do this. But I want to remind you that we have experience with some planetary-like samples in the lunar science program. And lunar science really was transformed after the Apollo astronauts returned samples to Earth. The reason that we want to do this, of course, is that laboratory analysis of samples allow analytical capabilities that cannot be matched by remote sensing. For example, sophisticated sample preparation, use of instruments that cannot be miniaturized, discovery responsive investigation pathways. And return samples are the gift that keeps on giving. We are still analyzing lunar samples more than 50 years later and making new discoveries because some of these samples have been curated and are preserved for future generations, which can use analytical techniques that were not invented at the time that the samples were returned. Of course, it matters where and what you sample. Some people may say that trying to constrain an entire planet's geology using samples from a single site is really not possible. Well, to some degree, you certainly cannot do everything with samples from one site, but terrestrial geology demonstrate that samples from well-chosen localities provide data of profound global significance. The Jezero Crater Collection site, which has been interpreted as a Noachian paleo lake, the period before about 4 billion years ago, a paleo lake within a crater in petrologically complex basement, represents a critical time interval that is particularly important from a geologic and possibly biologic perspective, and from a time not represented by Martian meteorites. The site contains both igneous and sedimentary units that are carefully chosen to address a variety of critical questions, which I'll talk about in just a little bit. But before we do that, you all know that we have Martian meteorites. It surprises me that we're approaching 200 of these samples now. Although I will say that many of those are paired meteorites, so we don't have 200 different samples. But And many of them are paired, not in the sense that they fell together, but they were ejected from Mars at the same time. We can make that interpretation based on the Mars ejection ages. And you see some examples in this diagram here. Samples that have the same petrology, the same mineralogy and petrology, that is, they're the same type of Martian meteorite, a laserlitic sugartite or an alkalite, for example, have the same ejection age, so they are presumably, they were ejected from the same location. And if we look at these relatively well sampled sites, plus we have some individual meteorites that don't have other pairs, but either have distinct petrology or a distinct ejection age. We have perhaps 10 separate launch sites, but they are from unknown locations. These are biased compositions. With one exception, all Martian meteorites are mafic or ultramafic igneous rocks, and that one exception is an ancient regolith breccia that is composed of igneous fragments. And they have biased, that is, mostly young crystallization ages. Almost all of them are Amazonian, the most recent period in Mars history. And that likely is a function of the fact that they have been launched by impacts, and the impact mechanism launches spalls near the surface, relatively near the surface, and we think that the target has to be made of hard, coherent rocks to be able to transmit the seismic wave with enough fidelity to accelerate samples to 5 kilometers a second, the ejection velocity. And most of these meteorites are heavily shocked, and some are weathered or contaminated. So it's a biased collection. It's very important, but it doesn't tell us everything. We know that because there are lots of sedimentary units on Mars that are interpreted as either fluvial, lacustrine, evaporative, or aeolian, as well as hydrothermal sites and pyroclastic rocks. And none of these have been sampled as meteorites, probably because they don't have the strength to survive acceleration to 5 kilometers a second. And some of these, of course, are the most likely samples to contain organic matter and biomarkers. Well, what about Mars rovers? They have accessed many of the sites containing those kinds of rocks, but the types of analysis that can be done by rover instruments are limited, of course. Most of these locations are sedimentary, some are igneous, all are ancient, mostly Noachian sites, and there are only a few landing sites: Aris Valles, Gusev Crater, Meridiani Planum, and Endeavour Crater, sampled at the same site, basically, Gale Crater, and Jezero Crater. So let's take a stab at what discoveries we expect can be made with returned Martian samples. And I'm not just giving you my ideas here. I'm channeling a report, but that was completed by 92 planetary scientists, some of whom are probably listening in here, from 17 countries. And this report was by the MSR Objectives and Samples team, and it was published in Meteoritics and Planetary Science, or at least a shortened version of it, published in MAPS, and then it's available online. So we're going to look at 7 different important questions that we have not fully resolved, or in sometimes resolved at all, using remote sensing and meteorite data, but which these carefully selected Martian samples that have been chosen by the Perseverance rover team to address these questions may be able to do. So the first question is, does extraterrestrial life exist, or has it ever existed in the solar system? If so, when, where, and what are or were its attributes? The challenge in life detection is not just to be able to detect relatively obvious life forms, but to recognize ambiguous evidence. Life detection is a process. It's not just a yes-no test. And MSR will allow us to use the entirety of Earth's laboratory capabilities, optimizing the chances of detecting and correctly interpreting subtle signals. Here you see the kinds of tests that can be detected, can be used, and all of them will be utilized, and a diagnostic biosignature will probably have to involve more than one of these tests, maybe all of these tests. Uniquely establishing evidence for extinct life is especially challenging, involving a combination of field and laboratory studies to document habitability, to assess the preservation potential for biosignatures, and to document the absence of terrestrial contamination. Laboratory investigations require organic extraction protocols, like what you see on the left of this slide, and molecular stable isotopic characterizations that are only possible in terrestrial laboratories. For extant life, the requirements for laboratory analysis protocols are even more stringent, requiring careful sample handling that precludes contamination with terrestrial life, as well as documentation of metabolism or respiration and of reproduction in culture experiments. And the way that's done, that investigation pathway is discovery dependent, as you see on the right side. We don't know what form life might take, whether it would be alive upon return to Earth, its ability to grow and metabolize on the Earth, whether it's related to life on Earth. And so the answers to those questions dictate downstream experiments. So it ends up being a very complicated set of experiments that are difficult to do. And I have to mention here the Allen Hills 84001 Martian meteorite, which, as all of you I'm sure are aware, contained organic matter, peculiar minerals, and some intriguing morphologies that were suggested to be evidence of extraterrestrial life. All of the evidence has eventually been shown to have abiotic origins. But if we didn't have this sample on the Earth to manipulate in the laboratories, we wouldn't have enough information to even pose the question of whether or not it might contain evidence for life. So this is, I think, a good example of why we need samples to evaluate the question of extraterrestrial life. The second question is, how and where did prebiotic organic chemistry occur, and what role did it play in establishing the required chemical context for the origin of life? One necessary condition for life's origin, in addition to water and a source of energy, is the availability of appropriate organic compounds. We have very little knowledge of this from Earth, but the ancient organic record of Mars may be better preserved, as suggested from studies of Martian meteorites and analyses by rovers. sedimentary analyses that have been carefully selected by the Perseverance rover team on the basis of their potential to acquire and preserve organic matter, as opposed to random samples launched as meteorites, will allow a much better opportunity to understand the complexity of prebiotic chemistry. So MSR will allow us to determine molecular structures, as you see on the left side, including optical isomers, as you see that is different geometric forms, as you see on the right-hand side, which, by the way, life as we know it employs. And it will allow compound-specific isotope compositions of organic compounds. And this will go a long way towards helping us understand the prebiotic chemistry record that we also see in carbonaceous chondritic meteorites. Third question is, what is the history of habitable environments on planets in our solar system beyond Earth? Defining planetary habitability is complicated. It requires information on the timing of accretion, stellar and impact fluxes, orbital stability, as well as the role of planetary bulk composition versus size in setting the pathways for magmatic, tectonic, magnetic, and atmospheric evolution. All these things have something to do with habitability. Within our solar system, it's been argued that Mars exclusively preserves the geologic record needed to understand the early evolution of habitability. 5 geologic environments are presently recognized as potentially habitable and capable of preserving evidence of habitation. They are a sedimentary system, hydrothermal system, a deep groundwater system, locations that experienced water, rock, atmosphere interactions, and iron-rich springs. Jezero crater contains an ancient sedimentary system of lake bed and deltaic deposits. So there are a couple of those already. And then basement rocks in large craters, and the basement here is accessible as samples from the Jezero crater rim, are commonly affected by hydrothermal fluids. So there's another possible habitable system here that can be accessed. Volcanic samples in Jezero are less likely to serve as habitable environment, but to the extent that they have undergone aqueous alteration, they may contain organic traces of life as well. Jezero crater exposes an ancient sedimentary system with lacustrine and deltaic and possible hydrothermal deposits, and thus qualifies as a potential habitable environment that experienced climate change. So it's a pretty good place to look to address this question. MSR can allow measurement also of trace elements, volatiles, stable and radiogenic isotopes that define environmental conditions and timing. And samples can also allow the complete characterization of minerals and amorphous phases. I remind you that amorphous material comprises about 30% of Mars soils, and all of these materials may be indicative of particular environments or conditions. The fourth question is, how did planets form, differentiate, and evolve as geological and geophysical bodies? Much of what we now surmise about Mars' geologic evolution and internal composition comes from Martian meteorites. But analysis of igneous rocks by rovers indicate a less biased and more expansive view of Mars' igneous rock compositions. Samples collected in Jezero crater include ancient basaltic and ultramafic rocks, in addition to all those sediments, that will provide a thermochemical record of the planet that's not presently accessible, and it'll serve as a new window on its interior. the trace element and radiogenic isotope compositions, and the magnetism of young Martian meteorites have all been studied, and they provide a view, but an incomplete view, of early differentiation in the planet's interior, as well as its evolution. But we can expand that by being able to study these very old igneous rocks and hopefully get a more complete view of planet formation, differentiation, and evolution. Another thing we should be able to do is have a perhaps better chronometer for use throughout the solar system. On Earth, there really are no rocks preserved from the first period of geologic history, but pre-Noachian and Noachian rocks are preserved on Earth, and more importantly, preserved as igneous rocks on the floor and rim of Jezero crater. And to the extent that we can compare radiogenic isotope ages of these igneous rocks, that is, hopefully crystallization ages of these igneous rocks, with their crater density record, then this can be a new calibration points for Mars chronology and allow us to better understand the flux of impactors outside the Earth-Moon system. Right now, we use the calibration of lunar rocks, which is very good for objects throughout the solar system. But we don't know that the flux of impactors in the Earth-Moon system necessarily applied to places outside that system. And this will allow us to test that. So that can be a very important part of what these Mars rocks, return Mars rocks, can do. Fifth question: can we use early geologic and geochemical records throughout the solar system to interpret how planetary growth and dynamics controlled or altered the distribution of planets and planetesimals during the first billion years? This is something that Ed Scott was very interested in and actually published a seminal paper on this. Nucleosynthetic isotope anomalies in meteorites and planetary samples, you see an example of that in the diagram on the left, indicate distinct reservoirs in the early solar system. The reservoir that includes the Earth, that is the non-carbonaceous reservoir, is shown there on the left, and then the carbonaceous reservoir is shown on the right. This is hypothesized to have been separated by the rapid growth of Jupiter, as shown on the right-hand side. And the analyses of, well, notice there is a Mars dot there that is based on Martian meteorites, but it would be very helpful to have separate analyses from return Martian samples. And analyses of these isotopes are tricky and can only be done in terrestrial laboratories. Also, instabilities in the motion of the giant planets in the first billion years may have scattered planetesimals, profoundly affecting the impact record of planets. Major questions remain about the timing and duration of large impacts, suggesting that the late heavy bombardment may not have been a spiked or singular event, or even if it existed at all. The ages of one or more impact events on Mars can potentially be quantified by radiogenic isotope analyses of return samples if they have been sufficiently shocked. There may have been samples that have been thrown in from distant areas, and if those are sampled, then we may be able to say something about large impact events on Mars as well. The sixth question is, how did planetary atmospheres form and evolve, and what are the processes that cause them to end up in such different states? You see what we know about the compositions of atmospheres based on non-radiogenic noble gases on the left. Return samples will include not only the modern atmosphere as a dedicated sample and as headspace gas in collection tubes, but also trapped ancient atmospheric gases in solid samples. Example is shown on the right. Some secondary minerals can also equilibrate with the atmosphere and thus be used to infer its composition. Major and trace elements, including noble gases, and not only their abundances, but also their isotopic compositions, can provide constraints on the origin and evolution of the atmosphere with possible implications for climate change. The amounts of species in low abundance can reveal information on the hydrologic cycle. The isotopic composition of gases such as helium and argon in basalts that have been cached in Jezero also have the potential to reveal details about the evolution and degassing of their mantle source regions. Understanding how the atmosphere has evolved is critical to constraining Martian volatile inventory and discerning how volatile species were originally acquired and have interacted over time with the planet. This information will play a significant role in comparison studies of other planets with atmospheres, such as Venus and even exoplanets. And finally, what are potential environmental hazards to future planetary exploration, and what kinds of in situ resources are available to support human exploration? Dust, regolith, and atmospheric samples can define an array of potential health risks in the Martian environment and prompt strategies to mitigate them. Knowledge gaps that must be addressed before human missions are possible require the thorough characterization of particulate and gas samples for toxicology, potential and chemical biologic hazards, and engineering assessments of corrosion, electrical effects, maneuverability, and structural integrity. In situ resources such as water and oxygen can mitigate the risk and cost of human exploration, and they might be addressed by knowing something about the Martian soil. And MSR can also inform mission hardware concepts for vehicle design and operations. The mission will break new ground in terms of technological firsts. And here is just a bullet list of some of those. Pinpoint landing of the most mass ever. The sample return vehicle is estimated to have twice the mass of any previous Mars landed mass. The first coordinated operations of multiple robotic vehicles on Mars, first launch from another planet, the first on-orbit rendezvous at Mars, first ground trip mission to another planet, the first return of samples from another planet. And you can see that the demonstration of some of these firsts would also be useful for human exploration missions to planets. The last thing I want to cover is, I want to say something about the synergy between samples and remote sensing data. I'm sensitive to this because some of the people in planetary remote sensing are not particularly supportive of Mars sample return, especially when they see the cost. And I just want to point out that there is a lot of synergy there, and both benefit from that. Here's an example. This is a wonderful GRS, gamma ray spectrometry map of the surface of Mars in terms of the elemental abundance of silicon. As meteoriticists, we're used to talking about silica. This is silicon, which is what GRS measured. And you see the range there, and then the Martian meteorite range in silicon. And they overlap quite nicely. The Martian meteorite range is a little bit broader, but they overlap quite nicely. And this would lead you to believe that at least at the core scale of GRS, there is a very limited variation in silica on the Martian surface. But sometimes they don't agree. And when we look at higher spatial resolution, there are some examples of fractionated, that is, silica-rich or feldspar-rich rocks that do occur locally. Here are some examples: a possible dacite flow in the Nili Patera caldera. There's some feldspathic rocks that have been identified in Milwaukee's Terra from visible near-infrared spectra. There are what have been called quartzo-feldspathic rocks in Syrtis Major in these two craters, although later studies indicate that they're not really quartz-bearing. They are containing silica, and it may be an alteration product rather than quartzo-feldspathic, that is, granitic rocks. And then there are feldspathic and siliceous rocks that bear tridymite in Gale Crater on the right. And finally, when they don't agree, ground truth can really help us understand remote sensing data. Here's the plot of silica versus FeO, and the boxes show the compositions determined by gamma ray spectrometer of various volcanic centers, volcanoes that are Hesperian, older Hesperian in age, as the cross-hatched boxes, and Amazonian or younger volcanoes in the dark blue boxes. And because of this difference in silica, it's been suggested many times that perhaps these younger volcanoes, the lavas are ultramafic lavas. The two black circles on here are Rover data for Hesperian lavas in Gusev Crater at two different sites with, those are not error bars there, they represent the range. But you can see there's overlap between the Hesperian rocks that were analyzed by rovers and the volcanoes. But look at all of the blue dots, which are Amazonian Martian meteorites. Those have to come from those blue volcanoes in the bottom. But there is a significant difference in silica content. All of the Martian meteorites have higher silica content than the volcanoes that they must come from. The explanation is that these Amazonian volcanoes are covered with dust. The dust deposits have been suggested to be as thick as a meter. That may be an exaggeration, but there's a lot of dust on these volcanoes. And we now know the composition of Martian dust. It's been analyzed by rovers, and it's about 38 to 40% silica. So off scale on this diagram. So if the GRS is analyzing dust or some combination of dust and the underlying lavas, then you would get these low silica contents. So That's the explanation for why there is a difference, but it shows you how important ground truth can be in correctly interpreting remote sensing data. So let me summarize the bottom lines here. The rocks in Jezero crater have been judged by the scientific community as among the best accessible recorders of the early geologic and possible biologic history of Mars. The scientific value of Mars sample return has been documented by 2 prior decadal surveys and newly reiterated by the International Mars community, the International Mars community. The partnership of NASA and ESA demonstrate in this Mars sample return effort demonstrates broad international support for returning these samples. The return samples will be a scientific boon to those who are lucky enough to receive them, but for generations to come, as well as these samples will be curated for a long time. And the return dust and atmospheric samples will be used to address knowledge gaps that really should be filled before human exploration. So it's time to finish what we started. Mars sample return is in trouble right now, and it's important that the community that is going to benefit from this express its support in making sure that we actually complete the missions that will be required to do that. So that's it. And I will turn it back to
Well, thanks very much, Hap. That was a wonderful review of the state of affairs and what we know about Mars and what we really do hope we can continue to do. What I'll do now is to open up the chat box, and those of you in the audience who have questions, you should be able to type your questions into that. And that there, is that open?
Yeah.
Okay, so it takes time to type. So while we're doing that, Hap, I take it you would like to go to Jezero crater number 1.
Well, that's already been decided. We're going to Jezero crater. The
Okay,
Perseverance rover is collecting and caching samples as we speak in containers that can be returned safely to Earth. So that decision's already been made, and so yeah, we'd sure like to have these Jezero samples back.
Very good.
So here's a message. I'll just read it out. Can you say more about how MSR is in trouble and how the scientific community can best signal support? The MSR project had a health check about 6 months ago, I think, maybe not quite that much. And although the evaluation team said a lot of good things about the planning for the mission, they were concerned that NASA had not planned for the real cost of the mission, probably something that afflicts every large NASA mission. And this is a combined NASA-ESA project, and which takes a lot of coordination. And they were also concerned that maybe the coordination wasn't as good as it needed to be, and the management of the mission wasn't as strong as it needed to be. NASA is responding, and a team is working on a better economic estimate and perhaps a revision in how the mission is managed. And that report will be released, I think, in March, but relatively soon. And then we'll know how much it really does cost, hopefully, and can move forward. But in the interim, there are all kinds of issues with the entire U.S. federal government being funded, and big ticket items may fall by the wayside if there isn't sufficient support for them. So there are a lot of people who are doing things, Alex, to address this. There is an entire day of talks on the scientific value of Mars sample return at LPSC this year. There's a set of papers being written now for the Proceedings of National Academy of Sciences to make this case. There are a lot of people that are talking to NASA or talking to congressional staffers about this. But I think until this report is out, that's probably what we can do. And then after this report is available, then we'll see where we go from there. Shall I just go ahead, Ian? Okay. So the next one is from Clark Chapman. Nearly half century ago, Jerry Wasserberg promoted MSR as the most important future planetary mission. He opined that he could decipher the history of Mars from a single Mars sample. I think he did the same thing with the moon. He didn't believe SNCs were from Mars. Your talk shows why this is untrue. Do you think this view existed in the post-Viking 1970s? I don't know, Clark. I was actually very surprised when Jerry didn't buy that sugatites were Martian samples, but they have now passed all of the tests that we can possibly think of. And there's even been a rock, bounce rock, that was analyzed on the surface of Mars that looks an awful lot like a sugatite. I don't know how to respond more than that, but I think I agree with Jerry that MSR could be the most important future planetary mission, at least in the near term. But different people have different perspectives.
Okay.
Okay.
As Rianne Jones is asking something about silica, so I'll let you read the question out for everyone.
Okay. Does the silica-rich dust cover everywhere, or is just the Amazonian regions? Rianne, I think it's everywhere. Remember that the dust has been transported by global dust storms, by dust storms that are of global extent. It's very fine grained, and I'm sure travels many, 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 many kilometers. And so I expect that dust is the same composition everywhere. It's the same stuff everywhere. It's only been analyzed well by one Mars rover that where the dust collected on a collection panel and then was analyzed chemically I don't know about spectrally, but it was very good analysis. It was several analyses done at different times by this Mars rover, and the dust was basically the same composition both times, different dust storms and so forth. So I expect dust is the same everywhere on Mars, but it's a good question. Nancy Chabot asks, what measurement on a return sample from Mars are you personally most excited about? I really hope I'm alive when this happens. I'm increasingly worried about that, not from my health standpoint, but the fact that this always gets pushed downstream. You know, it's always been my whole career, Mars sample return has been 10 to 20 years downstream. And so the samples that are the measurements that I am most interested in are what I do. I'm most interested in understanding the petrology and geochemistry and chronology of the igneous rocks. But that's not really, well, the chronology is very important for a new age dating system, but it's the sedimentary rocks that are really the lodestone here that will address the most important questions. Of course, if there was any evidence for life, all of us would take that as the most exciting part of the mission. My fear is once this happens, it'll be a long time, if ever, before we get another set of Mars samples, unless there is evidence for life. And then I guarantee you we'll get some more. Okay, Don Brownlee asks, following Jezero, what would be your dream site? I don't know, Don. I think it depends on what is discovered, especially in the sedimentary rocks at this site. If they're found to be barren of life and maybe there isn't I think there'll be a good record of prebiotic chemistry, but if there isn't, then it might be really interesting to go to an igneous site. None of the landing sites for rovers have ever been chosen for because there were igneous rocks there. They've always been chosen because there were sediments there, and then there turned out to be igneous rocks there. In most cases, they were launched in by impacts, so they're float, they're not in place. But I'm not sure, and it'd be great to have everybody else chime in about what they think, but I'll guarantee you that a lot of the community was polled and weighed in on the Jezero site, and I'm sure that would be done again very carefully and thoughtfully if we ever had a chance to go to another site.
Right. I think is that the end of the questions on my chat, it seems to be.
That's all I've got.
That's all you have, yes. Well, I think that's a time to wrap up. And on behalf of all the participants who are, I'm sorry, kept in silence and invisible, I will thank on your behalf Hap for a wonderfully stimulating talk and a prospect of what might yet happen. I hope it does, and I know Hap does. And thank you very much for tuning in and making this whole exercise so worthwhile. I'm sure Ed Scott would have approved of everything that went on tonight. Thank you.
Thank you.